Hi, I'm Ozan Unal, and I'll be briefly introducing our work, Bayesian Self-Training for Semi-Supervised 3D Segmentation. In semi-supervised 3D segmentation, our goal is to improve a model's performance by leveraging unlabeled 3D scenes alongside a small subset of labeled data. Here we focus on a common approach to semi-supervised learning via self-training, where a model is iteratively trained on its own predictions. Of course, naive self-training is prone to confirmation bias. In this work, we will develop a pseudo-labeling strategy to reduce such a bias. At the core of our self-training framework lies a variational Bayesian approximation of uncertainty of the respective network's predictions via dropout-based Monte Carlo integration over multiple augmented versions of the original 3D input. This approximation delivers a more informed uncertainty estimate than simple confidence-based thresholding. We utilize both the estimated Shannon entropy from the sampled predictions and the predicted label from each sample to filter out uncertain or inconsistent points from the generated set of pseudolabels. While this formulation is sufficient for the task of 3D semantic segmentation, it does not work out of the box for instance-level segmentation, as Monte Carlo integration cannot be applied directly to instance predictions. More specifically, compared to semantic segmentation, where accumulation of labels can be easily handled across multiple stochastic forward passes, accumulation of predicted instance masks is not trivial and requires n-partite matching, which is NP-hard. To account for this issue, we propose a novel and efficient heuristic matching strategy across instances coming from different stochastic forward passes, based on linear sum assignment. Having matched predicted binary masks from individual stochastic forward passes, each resulting set of masks can then be treated as a set of two-class semantic segmentation outputs, and thus our proposed Bayesian pseudo-labeling can work directly. Similar to both semi-supervised 3D semantic and 3D instance segmentation, our proposed self-training formulation can easily be extended to include natural language prompts as input, and thus tackle semi-supervised dense 3D visual grounding, or in other words, referral-based 3D instance segmentation. A common technique when tackling dense 3D visual grounding is to employ a grounding by selection strategy, where first all instances are detected within a scene, and then a fusion module selects the best candidate based on the prompt. Using the same building blocks, we can reduce the task of dense 3D visual grounding to a set of two-class semantic segmentations, as in 3D instance segmentation, and a single-point semantic segmentation of I classes, with I denoting the number of total instances detected by the visual backbone. Thus, our pseudo-labeling strategy can be again used without modification. We demonstrate the effectiveness of our Bayesian self-training strategy for LiDAR semantic segmentation on SemanticKitty and ScribbleKitty, 3D instance segmentation on ScanRefer and S3DIS, and finally, 3D visual grounding on ScanRefer. Thanks for listening, and make sure to scan the QR code where you can find the project page for our paper.